Hello everyone, I am FADLA Mohamed Abdelilah, PhD student from Lagos University, and it's a great honor for me to stand here today and present my work about the stability and optoelectronic properties of phase pure and mixed halide PERC Sky in first principle in SI. So I will start by the solar energy. I will answer the question why the solar energy, why we choose solar energy, and then I will move to the perovskite material. I will describe their crystal structure and their different properties, and I will present the intrinsic properties that we can calculate it using abination method, and their relation with other extrinsic properties such as power conversion efficiency, and the problem that faces the perovskite material application for or commercialization, and then I will present our results about the lead-free halide perovskite. As you know, we are using the energy in everything in our life, in the space heating, water cooling, space cooling, and transporting, lighting, and everything in our life we use the energy. So we need a source of power, we need a source of energy. As you know about the pollution and the climate change, so we need a solution that without destroy our environment. So the best solution is the green energy, is the sustainable energy. But why the solar energy? For two reasons. We have a huge power source which is presented by the sun, as well as our country. Our country have a great place in the world. We have more than 2040 kilowatt per meter yearly, and we have the best, almost the best place in the world for the number of hours. So the perovskite solar cell. So what's the perovskite, or why the perovskite? The perovskite are very cheap, can be produced or elaborated at using simple solid solution process at low temperature with a high power conversion efficiency. Now it's equal to the silicium monocrystalline, and they are flexible, thin film, and flexible like the organic solar cell. All the perovskites have the same crystal structure or more distorted, but the ideal perovskite is a cubic structure, and now every compound has this crystal structure with APX3 chemical formula called perovskite. We can found at lower symmetry such as tetragonal and orthorhombic and rhomboedral crystal. So this the perovskite solar cell. As you can see, it is the regular and inverted perovskite solar cell. We have the electron transport layer and the hole transport layer, and the absorber is the perovskite material. As you know, after the sunlight excites the electron and create the carrier, what we call the exciton. It's the electron hole pair. So the hole and electron pair. So we need to separate these two carrier and then collect them by the anode and the cathode, and we produce the energy. So in my work I only focus on the absorber material, which the perovskite. So what we can do using abination method, we can calculate the band gap, we can do the band alignment to choose the band alignment by calculating the real maximum. For example, for the absorber we have the minimum, the maximum of the valence band and the minimum of the conduction band should be aligned with the whole transport material and electron transport material. So that's what we called the band alignment. To choose for this process is really necessary to choose a suitable partner for our absorber. We can calculate also the absorption coefficient and the exciton bending energy. We can also calculate the defect density and ionization level, and we can calculate the carrier mobility with not very simple, but it's not easy, but we can do that using ab initio method. And all these properties, intrinsic property, directly related to the power conversion efficiency, as you know, the open circuit voltage and field factor and the short circuit current. So what's the problem of the that limit the commercialization of perovskite material? The first is the stability. These compounds are not stable, only under ambient condition or temperature can be decomposed with toxic elements. So the toxicity of this compound, they contain the lead atom, and the scalability. Therefore, to resolve these two parameters, stability and toxicity, we use the tin atom and substitute the lead toxic atom. So this compound, cesium lead bromide perovskite, in the orthorhombic structure. So as you can here, we calculate the volume of this unit cell, as well as the formation energy, and you can see here have almost the same formation energy. We improve their stability a little bit, but almost have the same energy. We also calculate their band gap or the band structure, and you can see we improve the band gap, for example, with 70% from of lead are suitable with the silicon tandem solar cell, perovskite silicon tandem solar cell, and this it's really suitable for the single junction solar cell. And you can see this compound have almost the same band structure. Here I calculate the effective mass in different direction, in this direction gamma to Z and gamma to F direction. As you can see, for the electron, for the hole, we have isotropic character of the effective mass, but for the electron effective mass we have high anisotropy in the GF direction. In the G gamma F direction, you can see the effective mass are equal to 0.2, and for the Z direction, the effective mass is much higher, 1 point. So this for this part, the compound, when we synthesize our compound, you should take care in this. It can destroy the solar cell and limit their efficiency. So I finish, and thank you, and if you have any question, please don't hesitate and contact me. Thank you.